Hi all, welcome to the third lecture on electromagnetics. So in this lecture, the main topics that we're discussing are wave equation in phasor form. That is the first part. And actually the wave equation in phasor form is the last portion in module 5. Okay. And from there, the next topics that we are going to discuss are about plane waves in lossy dielectric, lossless dielectric, free space, and good conductors. Okay, so the second set of topics listed here are actually part of the sixth module, but they all come under the topic electromagnetic waves. So it is actually a continuation of wave equation in phasor form itself. So from this point, the last portion of the fifth module, we'll be directly entering into the sixth module because those portions are continuous. Okay. So now one main thing is before we go into the derivation of the wave equation in phasor form, okay, the first three slides that I have over here, this is for a basic understanding. Okay, that is in order when we derive the wave equation in phasor form, before we derive that, there are some basic things that you need to know about the application of phasors to electromagnetic fields. So the first three slides in this lecture, I'm going to cover those basics. Okay. So the first thing that we need to know is we know that an electromagnetic wave, okay, it is formed as a result of interaction of electric field and magnetic field. And each of these fields, okay, both the electric and the magnetic field, they are actually time harmonic fields. What do you mean by a time harmonic field? It is a field that varies periodically or sinusoidally with time. Okay. So basically, electromagnetic waves have the property that they are composed of time harmonic fields. So before applying phasors to electromagnetic fields, we're going to review some basic concepts here. So as you can see, we have the first thing that I've written down is the basic expression, which all of you would be probably familiar with. Okay, see, this is the expression for a phasor. Supposing I have a phasor Z, we know that a phasor is a complex number. So how is it going to be represented? It will be represented as x plus jy. Or another way, in polar form, this is in the rectangular form. In polar form, how can you represent it? We can represent it as r angle phi. Okay. Yet another way of representing this r angle phi is to write z as z is equal to r e raised to j phi. Okay. And this is further expanded and written as r cos phi plus j sin phi. I'm sure you're familiar with these equations. Okay. So what does this magnitude r stand for? It is the magnitude of z, which is root of x square plus y square. And how do you find out phi? Phi is tan inverse y by x. And what will the complex conjugate of this z be? It will be x minus jy. So what happens to the angle? The angle is written as minus phi. And in polar form, again, it is written as r e raised to minus j phi. So these are some very basic concepts about representing a phasor. Now what we're doing here, now we are discussing about electromagnetic fields which are time harmonic fields. So we need to introduce the time element. So what happens is, see, when you introduce the time element, what happens is your phi here, okay, the phi which we're referring to, it is actually omega t plus theta. Okay, when you introduce the time element, I'm going to write phi as omega t plus theta, where this theta, it could be a function of time or space coordinates or a constant. Okay, so supposing I'm writing phi as omega t plus theta, then what happens when you split and write it as a real and imaginary part of phi? This again you're familiar with. See, r e raised to j phi is there. In place of this phi, What am I going to substitute? I'll substitute omega t plus theta. So what does this become? It can also be written as r e raised to j in brackets theta plus omega t, which can further be written as r e raised to j theta into e raised to j omega t. Okay, so this again, how can it be written? It can be written as r, okay, cos omega t plus theta plus j sine omega t plus theta. Okay, this equation 9.63 can also be written as small r cos omega t plus theta plus j sine omega t plus theta. So what is the real part of r e raised to j phi? The real part will be the cos term, r cos omega t plus theta, and the imaginary part is going to be r sine omega t plus theta. So what does this imply? Supposing I'm representing a current I of t, so that is the instantaneous value. If that is represented as I0 cos omega t plus theta, what is this implying? This implies that this particular expression for I of t, it corresponds to the real part of I0 e raised to j theta e raised to j omega t. How can I validate this or prove this? This is based on these equations that I just explained, equations 9.63 to 9.64b. Based on these equations, if I of t is I0 cos omega t plus theta, that particular I of t corresponds to the real part of I0 e raised to j theta e raised to j omega t. Similarly, supposing I have another current I dash t, which is represented as I0 sine omega t plus theta, that will correspond to the imaginary part of I0 e raised to j theta e raised to j omega t. Okay. Now, so this complex term that I have over here, I0 e raised to j theta, okay, which results from dropping the time factor e raised to j omega t. So what you should understand here is, okay, when you introduce the time factor, the term which is contributing to the time factor is the omega t. Okay, omega t is the term that contributes to the time factor, which means e raised to j omega t represents the time factor. So the other term, that is the term I0 e raised to j theta, which results from dropping the time factor e raised to j omega t in I of t, that is referred to as the phasor current. Okay, and that will be denoted as IS. So what does that imply? How can I write IS as? IS can be written as I0 e raised to j theta or I0 angle theta. Okay, so the subscript S, IS, the subscript S denotes the phasor form of I of t. So I of t is the instantaneous form and I of S is the phasor form. And how are these two related? The instantaneous form is equal to the real part of the phasor form into e raised to j omega t, where e raised to j omega t is the time factor. Okay, so why this is important is, now when we actually derive the wave equation in phasor form, the electric field and the magnetic field, it is easier to represent in terms of phasor form because your field is time harmonic. So by eliminating the time factor e raised to j omega t, I'm going to use the notations, or we will be using the notations ES, okay, E subscript S and H subscript S to derive the wave equation in phasor form. So that is why we are studying these basics also. So I hope it is clear till equation 9.66. Okay. So that was, we had taken the example of a current. So in general, supposing I have a vector A, okay, that is, it could be an electric field or a magnetic field, which is represented as X, Y, Z and T. What does that imply? It has space coordinates, that is a position, and also a time. It is a time varying field. Okay. The phasor form of A, which is AS. So there we are dropping the time factor. So actually, what do you mean by the phasor? Phasor is, if you have a time harmonic field, okay, when you eliminate the time factor, what is remaining? That is the phasor form. Okay. And what is the relation between this vector, that is the instantaneous form, and the phasor form? General expression is that A, is equal to the real part of the phasor form into e raised to j omega t. So supposing I have an instantaneous value a, which is represented as a0 cos omega t minus beta x ay. Okay, how can this a be written as in terms of the phasor form? That is, this a can be written as the real part of. So how do I write this? See, already we have discussed, if you have the cos term, it corresponds to the real part of a0 e raised to minus j. So this cos part is the real part of e raised to minus j beta x. Ay is written again, and then the time factor is also there. Okay. So if I compare equations 9.67 and 9.68, what does that imply? What is AS equal to? AS is actually equal to A0 e raised to minus j beta x ay. So this is the phasor form for a vector A. For a vector A which has x, y, z and a t coordinate. The phasor form is given by equation 9.69. So what does this imply? What you should understand is, when you're converting, okay, in order to obtain the wave equation in phasor form, what we're going to do, we have our general wave equations or general Maxwell's equations. In those equations, all expressions of the form dou A by dou T, that is going to be replaced as j omega as. And all equations of the form integral A dot T, that is going to be replaced with as divided by j omega. Okay. Actually, these two equations I had also discussed in the fourth module. See, in the fourth module, there was a topic on Maxwell's equations in phasor form. So when we discussed about Maxwell's equations in phasor form, I had mentioned this, and those equations were given to you also. Okay, it is there for you to study. Please go through those equations as well, because the wave equation in phasor form is actually going to be derived based on Maxwell's equations in phasor form. So you should be knowing those equations. Those who have forgotten, please look up your textbook or your notebook and go through those equations also. Okay. So this is how the relation holds true. Okay. So these were some basics that you had to know in order to derive the wave equation in phasor form. Now we're going to actually start the derivation. So what is our topic? The topic is to derive the wave equation in phasor form. So see, here also the approach is just the same. In the previous lecture, in lecture 2, we had derived the general electromagnetic wave equations from Maxwell's equations. Okay. And what did we do there? I had mentioned that lossy dielectric is the most general form. Okay. So if we can derive the equation for the lossy dielectric, okay, by suitably substituting the value of sigma, epsilon and mu, the wave equation can be obtained in any other medium. This was already mentioned in lecture 2. So the same thing here also. What we're going to do is, in order to derive the wave equation in phasor form, what we're going to do is, we're going to first derive the wave equation for a lossy dielectric. What is a lossy dielectric? A medium where when your electromagnetic wave propagates, okay, there will be some losses, okay, due to poor conduction. So another name for a lossy dielectric is, it is an imperfect conductor or an imperfect dielectric. That means it is a partly conducting medium. A lossy dielectric is a partly conducting medium where your sigma is not equal to 0, epsilon is equal to epsilon r epsilon naught, and mu is equal to mu r mu naught. Okay, these are things which are discussed in lecture 2. So first we are going to derive the wave equation for a lossy dielectric. So see, basically what we're doing is, we have to derive the wave equation in phasor form, which we are going to derive for general case will be for lossy dielectric. Okay, and then the same expression is valid for any other medium. What are the other mediums? Lossless dielectric, free space and a good conductor. Okay, for any medium, this equation will be valid. The only thing is you need to suitably substitute for sigma, epsilon and mu. Okay. So in this lecture, what we're going to do is the basic wave equation in phasor form we're going to derive. And then what you'll understand is the main term that we derive, okay, or see, I'll just go to that equation. See this equation here, equation 10.17 and equation 10.19. These are the two equations that represent the wave equations in phasor form. And this is an important thing. The wave equation in phasor form is also referred to as vector Helmholtz equations. Okay, the wave equations in phasor form are referred to as vector Helmholtz equations. So what you have to understand is this is the general case. Okay, so here you have gamma, which is the propagation constant. And there is an expression for the propagation constant as well. So what you can understand is we are actually going to, for each medium, the basic wave equation will derive, and then we're going to derive the expressions for the various constants. See, that means in order to write this wave equation, if you know the propagation constant properly, it is possible to write the wave equation. And propagation constant is alpha plus j beta. Your propagation constant gamma is alpha plus j beta, where alpha is the attenuation constant or attenuation factor and beta is the phase shift. Okay, so for each medium, we are going to obtain the expressions or write down the expressions for alpha, for beta, for the intrinsic impedance, okay, for the velocity. Alpha, beta, intrinsic impedance and the velocity. These are constants which are already defined in lecture 2. Okay, so the main the main part of this lecture is, once we generally derive the vector Helmholtz equation, what do we infer from that? We infer that if the constants of the medium are known, automatically the equations can be obtained. So all these constants are going to be obtained for the different medium. That is what we're going to do. Okay, so let's start. So again, we are considering, so a lossy dielectric is a linear, isotropic, homogeneous medium that is charge-free. What do you mean by charge-free? Rho v is 0. Now, this is where the importance of the phasor form comes in. We are assuming and suppressing the time factor e raised to j omega t. So Maxwell's equations in the previous chapter, this is from Sadhku textbook. So Maxwell's equations in phasor form. This table 9.2, what they are referring to is, the table number may be different in the new edition of Sadhku. So please look up accordingly and go through those equations. So the equations 10.11 to 10.14 are actually the wave equations. 10.11 to 10.14 is the Maxwell's equations in phasor form. So Maxwell's equations in phasor form forms the basis to derive the wave equation in phasor form. So since we are eliminating the time factor, we are using the terms ES and HS, which stands for phasor form of electric field and phasor form of magnetic field. So del dot ES and del dot H both will be 0 because the medium is charge free. Del cross ES, actually what is this equal to? It is equal to minus dou B by dou T, where your B is written as mu H. In this case, it is mu HS. I already told you the dou by dou T term is going to be replaced with j omega. So that is how you get equation 10.13. Then again, del cross HS is equal to J which is sigma ES plus dou D by dou T. Again, the D can be written as epsilon into ES. And the dou by dou T term is replaced with j omega as explained earlier. So the basic Maxwell's equations are written in phasor form and the derivation starts from here. Now for equation 10.13, I'm going to take the curl on both the sides. Okay, so the curl is applied on both the sides. Now what happens is, we also have a vector identity here. 10.16 is a vector identity. So if you see, this derivation is very similar to the wave equation derivation that we dealt with in lecture 2 also. Okay, only thing is now we are doing the representations in phasor form by replacing dou by dou t in terms of j omega. That's all. So so here in place of this identity, I'm going to replace it with ES. So when you replace it with ES, this del dot ES term becomes 0 because as per Maxwell's equation 10.11. So I'm left with the remaining portion. Okay. So I get equation as shown here. Then from this point, what happens is, see this particular term here, okay, that is j omega mu into sigma plus j omega epsilon. This part, I'm going to replace it with the constant gamma, which is called the propagation constant. So then how can I write this expression? So this is gamma square. Sorry, I'm going to replace this with gamma square. So gamma is actually equal to square root of this particular term. Okay, that is how I'm defining the propagation constant square. Okay, gamma square is equal to this particular term. So if this is written as gamma square, okay, and I take it to the other side, how can I write this expression? It can be written as del square ES minus gamma square ES is equal to 0. So this is one equation. Gamma is your propagation constant, okay, in per meter of the medium. Using a similar approach, okay, that is, we are going to take the curl. Similar approach, what will the similar approach be here? I'll be applying the curl to equation 10.14. And then, so when you get a del cross ES over here, that will be replaced from this particular expression. Then again, you will apply this identity and then rearrange the equations a little. Okay. So when you do that, you're going to get a similar expression for in terms of HS also. That is equation 10.19. So these two equations, 10.17 and 10.19. These two equations are referred to as the wave equations in phasor form, and they are commonly known as the homogeneous vector Helmholtz equations. Okay, so this is important. What do you mean by vector Helmholtz equations? They are the wave equations which are derived in phasor form, and the derivation is just explained now. Okay, so the only difference here is as the medium changes, like for example, when you have a perfect conductor, your sigma becomes 0. So in that case, this gamma square term reduces to just this part. Okay, that is, it will have only the j omega mu into j omega epsilon term when this term becomes 0. Okay, so we'll see those derivations. So I hope till here the derivation is clear. Now what we are going to do is, we are going to derive expressions for one by one each medium. Those constants that I mentioned, we are going to derive. Okay, so please understand this. These two equations, 10.17 and 10.19, is applicable for any medium. Okay, so when you're asked to derive the wave equation in phasor form, derive this. Then depending on the medium that is asked, you have to show the derivation of the other constants. That is, how to derive alpha, how to derive beta, what is the expression for the velocity of propagation, and what is the expression for the wavelength and the intrinsic impedance. These 5 constants for each different medium. Okay. So first we are going to start with the derivation of alpha and beta for the lossy dielectric, because that is the first case that we are considering. See, this gamma is defined as alpha plus j beta. Now, for a lossy dielectric, this is the expression that we get for alpha and beta. How these expressions are obtained, I've given it to you in the next slide. I've written down the steps. Okay, see, this is very self-explanatory. Okay, I'm just going to very briefly explain. Please go through it on your own. If there's anything that needs clarification, you can ask me. So we are starting with your gamma. Gamma is alpha plus j beta. Okay, gamma is alpha plus j beta. Alpha is the attenuation constant, beta is the phase constant. Now, from our particular vector Helmholtz equation, we have defined gamma in this way. So you're just opening the brackets, okay, So this becomes the real term, and then plus j omega mu sigma. So if you're writing it as gamma square, the root sign will be taken out. Now what happens is, so this is gamma square. Here I have a gamma square written as alpha plus j beta. So what is alpha plus j beta square going to be equal to? If I want to equate this equation and this equation, when you square alpha plus j beta square, you're going to get this. That is equal to this part. So from here, the real part and the imaginary part I'm going to equate. Okay. Now, so I got an expression for alpha square minus beta square. Now I want to get an expression for alpha square plus beta square also. So what I've done is, see, if this, you're defining it this way, what you do is, in order to prove that this right hand side is equal to this left hand side, just expand this and you're going to get this. Okay, you try it out for yourself. When you expand this part, you're going to get this. And what we're doing here is, in place of alpha square minus beta square, you already have an expression over here. You just square this and write it over here. Similarly, for 4 alpha square beta square also, you square this term and write it over here. So this gives you equation 1, alpha square plus beta square. For alpha square minus beta square, already the equation is there. Do 1 plus 2. When you do 1 plus 2 and simplify, you're going to get the expression for alpha. And when you do 1 minus 2, you're going to get the expression for beta. Okay. See, it is important that you know these final expressions because you may get problems also to solve. Okay. So this is the expression of alpha and beta for which medium? For a lossy dielectric. Please remember these two expressions are for lossy dielectric. Then V. What is V? V is the velocity of propagation, which is omega by beta. This was already explained in lecture 2 also. And lambda, which is the wavelength, that is defined as 2 pi by meter. The unit here is meter. Wavelength, the unit is meter. For velocity of propagation, it is meter per second. Okay, so far we have derived the alpha and beta, the attenuation constant and the phase constant for a lossy dielectric medium, and we've also written the expressions for the velocity of propagation and the wavelength. Now we're going to derive the expression for the intrinsic impedance in the case of a lossy dielectric. So how do you derive it? Sorry, before we derive the expression for the intrinsic impedance, there's one more thing. Okay, that is so we've derived till here. Okay, we've derived alpha, beta, V and lambda. Now the next thing is, so we already know this. We are assuming that your E, electric field, has an X component, isn't it? That is how we are assuming. E, the component of the electric field, is the X component. So ES, because now we are dealing with the phasor form. Okay, so ES is actually EXS, where the X stands for the fact that it has only an X component, of Z, because your wave is propagating in the Z direction, and AX shows that the component of the electric field is in the X direction. So if I substitute this expression for ES in equation 10.17, what can I write it as? I can write del square minus gamma square of EXSZ. Okay, my equation 10.17 modifies to this form. Okay, so what is del square equal to? Dou square EXSZ by dou x square. Similarly, dou y square, dou z square, minus gamma square EXSZ is equal to 0. See, we know that since your wave is propagating in the Z direction, what does it imply? It implies that there can be a variation of the EXS component only in the which direction? Z direction. All the other directions, there is no change. So these terms become 0. Okay. So finally, you're left with this term. So here what happens is, I've just changed the partial derivative is changed to a full derivative. That's all. Dou square by dou z square minus gamma square of E excess Z is equal to 0. Okay, because there's only one component. So instead of dou, I've just written it as D. Okay, so you should understand that this is a scalar wave equation and it is a linear homogeneous differential equation. So I'm not going into the solution. You just need to know that for an equation of this form, for a linear homogeneous differential equation in this form, the solution will be like this: E excess Z. Okay, it will have a forward direction and a backward direction. Okay, so this stands for the wave propagation in the forward direction, and this stands for the wave propagation in the backward direction. Okay, so now we are going to consider the wave propagation only in the forward direction, which means I can assume that E dash 0 is equal to 0. Okay, for our assumption or for our derivation, we are going to consider the fact that the wave is propagating in the positive Z direction. So automatically E0 dash can be equated to 0. Okay. So in this equation 10.28, this term becomes 0 and I need to write only this term. Okay. So now what is happening is E of ZT. So E excess, it is the phasor component. So far I had used only the phasor form because I was deriving those equations. But if I want to get the final equation for the electric field, okay, then I need to introduce what? The time factor has to be brought back again, isn't it? So now there should not be any confusion, because in order to make this concept clear, that's why we have discussed those phasor concepts in the first 3 slides. So if you have any doubt, please go back and refer that once again. So the total E is actually the real part of E excess Z e raised to j omega t ax. Okay, I have brought back the time factor. Now here this is E0 e raised to gamma z, isn't it? What is E excess Z equal to? It is equal to, this term is 0. This term is 0. This is E0 e raised to minus gamma z. In place of this gamma, I'm going to write it as alpha plus j beta. Then what happens? I can write it this way, yes or no? E0 e raised to minus alpha z, and then the j terms combine together as e raised to j omega t minus beta z ax. And what is the real part going to be? It is the cos component. That means finally E of zt, that means the equation for the electric field, the final equation is E0 e raised to minus alpha z cos omega t minus beta z ax. Okay, and similarly, if I want to obtain the expression for the magnetic field, what is it going to be? For magnetic field, it will be the real part. In place of E0, it is going to be H0. Okay, and we have already, and this is going to be AY, because your magnetic field, the direction is in the component. Magnetic field has a component in the Y direction. So this is AY. Okay, it is written in analogy with EZT itself. And we know that H0 is related to E0 using this relation. H0 is E0 divided by eta. Okay, so now what you need to know here is, so far we've also got the expression, that is E of zt is fully obtained, H of zt the real part. Now in order to simplify this further, the expression for the intrinsic impedance is also needed. See, the intrinsic impedance again for a lossy dielectric medium, it is defined using this equation. So how this comes also, I'll just explain it. Okay, how we got this derivation for the intrinsic impedance for a, see, you should always remember intrinsic impedance is specified according to the medium. Okay, for a lossy dielectric, it is in this form. For free space and for lossless dielectric, it will be just root of mu by epsilon or root of mu 0 by epsilon 0 for free space and lossless. Okay, so we'll come to that a little later. So for now, we're going to derive this particular expression. So how do you derive it? So we know that your ES is EXSZ AX cap. Okay, here not the arrow, we'll use the cap notation. Okay. And we also know that EXS is written as E0 e raised to minus gamma Z. Now, what I'm going to do is, what is del cross ES equal to? Del cross ES, it has only the X component. That is why it's written over here. And this is 0, 0. And I'll write this. I hope you know how to write this. Okay. That is, we need to consider only the excess components. The other terms are 0. Okay, and then again, there is no variation with respect to y. So this term also becomes 0. So I have only this first term. And then in place of EXS, I'm going to substitute this also. So what do I get? I get, okay, so this is one expression. Along with this, based on Maxwell's equation, okay, del cross ES can also be written in this form. So I'm going to relate this with this term here. Okay, so minus j omega mu hs, that is equal to, when you differentiate this with respect to z, this is what you're going to get. So when you equate the magnitude on both the sides, what happens? Magnitude, what is the magnitude of hs? H0. What is the, and this side, the magnitude is E0 gamma. Okay, so I'm going to equate the magnitudes alone. So I will get j omega mu h0 is equal to E0 gamma, or h0 is equal to gamma by j omega mu E0. Okay. And by definition, how is the intrinsic impedance defined? It is defined as the ratio of E0 divided by H0. That means in this case it is J mu omega by gamma. So what you should understand, we are deriving the expression for the intrinsic impedance of a lossy dielectric. The unit I've already discussed, that the unit is in ohms. And we know the expression for gamma square. Okay, this is again from the equation. Right from the beginning, we have taken gamma square in this form. So gamma is square root. If I want to take the j omega mu out of the square, what do? I'm going to divide and multiply by j omega mu. So I take this out, write it in this form. See, these things are self-explanatory. Okay. So j omega mu by gamma. In place of this gamma, I'm going to substitute this. So finally, what do I get? The expression for the intrinsic impedance is, the intrinsic impedance of a lossy dielectric is square root of j omega mu divided by sigma plus j omega epsilon. Okay. And definitely the intrinsic impedance has a magnitude and an angle. Okay. So here, this is further, it's just modified and written. When you divide by j omega epsilon in the numerator and denominator, you get it in this form. Okay. So this form is written as magnitude and as angle. Okay. Okay. So see, the magnitude, numerator, the magnitude is root of omega by mu. I don't think that you should have any doubt in that. And the denominator is again of the form square root of a plus jb, or rather a minus, when you take this j on top, it becomes the a minus jb form. Okay. Or a minus jb can also be written as a plus in bracket minus jb. Okay. So when you take the magnitude of that, okay, it will be root of a square plus b square itself. So when you do that, this is what you're going to get. See, just write it down using that equation and you will get this answer. If you still don't understand, you can ask me personally. Okay. Because this is the basic conversion from a complex form into a polar form. That's all. And here again, tan In this case, the angle is tan 2 theta n. Okay, the angle here, which is sigma by mu epsilon. Okay, and the range for which theta n is defined. See, actually here, what does this theta n denote? It in a way it denotes the phase shift between E and H. And we know that the maximum phase shift that can happen is they are actually displaced by 90 degrees. So since we are writing it as 2 theta n over here, theta n can actually vary between 0 and 45. Okay, that is how the variation of theta n is defined. See, just one, probably one explanation that I can give you here is, see, any phasor of the form z raised to 1. See, supposing I have a phasor of the form z raised to 1 by n. Okay, z raised to 1 by n. Okay, where your z is of the form a plus jb. See, why I am talking about z raised to 1 by n is, see, if you see the numerator, there should not be any doubt. The magnitude here is root of mu by epsilon. Okay. For the denominator, it is of the form, your z here actually is a plus jb form. So this denominator is of that form, and it is raised to 1 by 2 in this case, square root. So raised to 1 by 2. In this case, the magnitude is actually given by r raised to 1 by n. Okay. R raised to 1 by n, that is the magnitude. So you just imagine, what is the r in this case? Root of a square plus b square, isn't it? So when you do root of a square plus b square, what are you going to get? You will get 1 plus sigma by omega epsilon the whole square root of that. Okay. R is square root of this. Then again, you have that r raised to 1 by n. So that is again raised to another 1 by 2. So it actually becomes 1 by 2 of 1 by 2. That is why you're getting a 1 by 4 over here. Okay, this is actually the explanation. I hope with this explanation it should be clear. Similarly, the angle part, okay, the angle part is actually written as cos. I don't have a mouse at home. I'm using the keypad. Okay, that's why I'm not able to write that clearly. I hope you can understand this. So this r raised to 1 by n cos, this is actually written as cos theta n. N is a subscript. Okay, cos theta n divided by n. This is the form. Similarly, plus j sine, okay, j sine theta n divided by n. This is the basic expression. Okay. So what happens is, in this case, this cos theta n by n corresponds to the 1. Similarly, this sine theta n by n corresponds to sigma by omega epsilon. Okay. So, so it is by n, and in this case, the n is, okay, so this is the form. So the n is 1 by 2. Okay, so it becomes cos 2 theta n plus j sine 2 theta n. And that is why you are actually having the tan 2 theta n over here. Because, I mean, in the denominator itself, I'm going to replace it as 1 by 2 and 1 by 2. Okay. And so that's how you get this expression. Now we're going to the next part. So far, what have we derived? We started with the vector Helmholtz equation, and then we derived the alpha, the attenuation constant and the phase constant for a lossy dielectric, and then we derive the expression for E, okay, and then the expression for H, the magnetic field, and then we came to deriving the expression for the intrinsic impedance. So this is just a waveform that actually shows you, see, if you see, this is the z-axis. So your wave is propagating in the z direction. Okay, the electric field is changing. If you see, it is changing in which direction? Positive and negative x direction. The variation in E is only along the x direction. So at t equal to 0 and at t equal to delta t, the variation with the instantaneous value. So this is how the variation can be drawn as a figure. Okay. So this is what I just explained now. We've derived. Okay. So now what we've done is, if you remember, we had written H as the real part of E0 divided by C. Now in place of eta, it has a magnitude and an angle, and then the remaining part. Okay. So that finally can be written as, what happens is this term is again brought to the numerator. Okay. So this theta n here, what does it actually represent? It represents the phase shift between E and H. And what does it imply? At any time, E is going to lead H. Okay. So this is the equation. The equation here, this is the equation that we have obtained for H. What was the expression for E? E was equal to E0 e raised to minus alpha z cos omega t minus beta z ax cap. And this is the expression for H. So it implies that at any time, E leads H or H lags E by theta n. Okay. That is, E and H are out of phase at any instant of time due to the complex intrinsic impedance of the lossy dielectric. Okay. So far, these the equation for the constants and the equation for E and H was due to the lossy dielectric alone. I hope it's clear till here. Now, the same thing, we're going to derive the expressions for a lossless dielectric. See, from the name itself, what do you mean by a lossless dielectric? A lossless dielectric is one, that is, it is actually a perfect dielectric. That is why conductivity is 0. Because the dielectric is perfect, your conductivity is 0. And see, this is the condition, okay? Your sigma is much less than omega epsilon. This is the condition for a lossless dielectric. It is a special case of lossy. Your epsilon is given in this way, mu is given in this way. So if I substitute these conditions into the equations for alpha and beta, okay? Sigma 0, epsilon and mu. So these conditions, if I substitute it, the alpha and the beta, that is, see, let's just go back to the expression for alpha. See here, alpha, if I give this as 0, what happens? See, if this term is 0, this becomes root of 1 minus 1. So this whole thing becomes 0. Okay. Similarly, for this term, what happens? If this becomes 0, this becomes 1 plus 1. So that is 2 root 2. And then finally, when I simplify that, the expression for beta that I'm going to get is omega root of mu epsilon. Okay, this is the expression for beta. The velocity of propagation is omega by beta. In this case, I'm just going to substitute this. So I get it as 1 by root of mu epsilon. So what does that imply? The simplified expression for the velocity of propagation for a lossless dielectric. Another name for the lossless dielectric is a perfect dielectric. The wavelength is again 2 pi by beta itself. Now here what happens to the intrinsic impedance? Again comparing it with the previous case. See here, if this is 0, what is the intrinsic impedance equal to? It is just root of mu by epsilon, isn't it? And here also this is 0. So the angle is 0. So what does this imply? For a lossless dielectric, okay, when a plane wave propagates in a lossless dielectric, the E and the H are in time phase with each other. There is no phase shift. E and H are in time phase with each other. Okay. Yeah, so that is what you're supposed to know about the lossless dielectric. Now coming over to the free space. So free space is again a special case, okay, where sigma is 0, epsilon is epsilon naught, and mu is mu naught. So whatever equations we obtained for the lossless dielectric here, in place of mu and epsilon, if you substitute mu 0 and epsilon 0, you will get the expression for free space. That's all. So alpha is 0, beta is obtained in this way. Okay. The velocity of propagation. So what do you understand from this? When a plane wave propagates in free space, it travels with the speed of light. So it shows that light is the manifestation. So this is how we can justify that. Is how can you justify that light is an electromagnetic wave? Because light is an electromagnetic wave that propagates in vacuum, and it has the same. So a plane wave propagating in vacuum has the same speed as that of light. Okay, so that is how we justify that light is characteristically electromagnetic. Then the expression for the wavelength, again 2 pi by beta. And how do you write the expressions for E and H? The intrinsic impedance, see this again we have defined, I've explained this in lecture 2 also. When you write it in terms of mu 0 and epsilon 0, it has a constant value, 377 ohms, intrinsic impedance of free space. Theta n is 0. So when theta n is 0, E and H, both are represented in terms of cos omega t minus beta z itself. Okay. This is only thing, this is AX and this is AY. So please remember, the same expression for E and H can be used in the case of lossless also. Both for lossless dielectric and for free space, the expressions for E and H can be written in this form because the phase shift is 0. Okay. Now, so the plot is shown here. See, if you see, this is the y direction, this is taken as the x direction, and this is taken. So your wave is propagating in the z direction. E is varying along positive and negative x, and H is varying along positive and negative y. The arrows indicate the instantaneous values. Okay, and we already know that you take the cross product. Okay, it will give you the third direction. So the generalized form was actually this. So AK stands for the wave propagation. Okay, AE stands for the direction of the electric field, and AH stands for the direction of the magnetic field. So wave propagation cross electric field gives you AH, AK cross AH gives you minus AE. Similarly, AE cross AH gives you AK. We had derived that when you derived the expression for the Poynting vector in lecture 1. The cross product of AE cross AH is going to give you AK, the direction of propagation of the wave. AK is the direction of propagation of the wave. Okay. So here, what do you understand from this? Both E and H fields, okay, at every point, they are normal to the direction of propagation, AK. That means the fields lie in a plane that is transverse or orthogonal to the direction of wave propagation. That is why such waves are called transverse electromagnetic waves, TEM waves, because the wave has no electric or magnetic field components along the direction. This also derivation we have seen. Ez and Hz are 0. Electric field only has a component in the x direction. Magnetic field only has a component, only has a y component. Okay, that is why they are called transverse electromagnetic fields. And each of E and H is called a uniform plane wave also, because E and H has the same magnitude throughout any transverse plane. Okay, and what do you mean by polarization? The direction in which your electric field points, that is referred to as the polarization of a TEM wave, that is a transverse electromagnetic wave, which means in our case, the electric field is polarized in the x direction. Okay. Now, one thing that you can also understand about, see, why I'm going through these portions quickly is all this is explained in much detail in lecture 2 about plane wave and the uniform plane wave. Okay. So this a uniform plane wave, it cannot exist physically, because ideally a uniform plane wave stretches to infinity. So it would represent infinite energy. Okay. So uniform plane wave is an ideal case, but where do we use them? When you talk about practical waves such as radio antennas and all, these uniform plane waves are good approximations. That is, any practical wave can be approximated to a uniform plane wave for various analysis purposes. Okay. So that's what you're supposed to know about wave propagation in free space. So one thing that you need to know is whatever expressions we have derived for plane wave and uniform plane wave in lecture 2. Okay, the derivation for plane, that was all corresponding to free space. That is, root of mu 0 by epsilon naught always corresponds to free space, and wherever we have taken root of mu by epsilon, that corresponds to lossless dielectric. Okay. And the next thing is the plane wave. Okay, see, I think the heading has gone out. It's plane wave in good conductors. Okay. This is plane wave in good conductors or perfect conductors. Okay, it's given over here. This is again another special case, a perfect or a good conductor. Okay, this is the last case, is one where ideally the conductivity is infinity. Okay, and epsilon is epsilon naught, mu is equal to mu 0, mu r. So sigma is much greater than mu epsilon. This is the last type of medium, which is a good conductor or a perfect conductor. Here again, if I substitute these conditions into alpha and beta, both alpha and beta will be equal, and this is the expression that I get. Okay, this is one way of writing, and this is another way of writing. That is, if I write omega as 2 pi f here, I'll get this expression. Then the velocity of propagation, again omega by beta. The beta is substituted from here. Lambda is, the wavelength is 2 pi by beta. So here again, for intrinsic impedance, when you substitute, the angle that you're going to get is 45 degrees. What does this imply? E leads H. That means for a perfect conductor or a good conductor, the phase difference between E and H is exactly 45 degrees. E leads H by 45 degrees. So this is the expression for E that you get. See, how do you get this? You know, you just go and substitute the value of sigma for the general case, that is this case here. In this expression, when you substitute, or rather in this, what does infinity stand for? If you have an infinity over here, what is your theta n going to be equal to? Theta n is going to be equal to 45. So that's how we get this relation. Similarly, this part also. So this is E, and when you write H, how do you write it? It is minus 45 degrees. Eta is substituted here in terms of eta itself. Okay. So see, till this point, let me just summarize whatever we have discussed in this lecture. We started with deriving the general vector Helmholtz equation, that is the wave equation in phasor form. So that is applicable for any medium. Okay. So when you're asked to derive the wave equation in phasor form, you can derive that. Only thing, for that particular medium, you substitute the sigma correctly. sigma, mu and epsilon has to be substituted correctly. That's all. Anyway, see, in the general expression, there's only a gamma. So you write down that expression and then below that, you start deriving alpha and beta for each case. Alpha, beta, the velocity of propagation, the intrinsic impedance, the wavelength, and expressions for E and H, that is the electric and the magnetic field. Okay, so we saw that for lossy dielectric, the phase shift can be by any angle theta n. For lossless dielectric, both are in phase. Okay, for a lossless dielectric, both are in time phase, E and H. For free space again, both are in phase, E and H are in phase. And for good conductors, the angle is exactly 45 degrees. And correspondingly, the expressions for E and H were also obtained. So till here you should know. So whenever you are asked to describe the propagation of plane waves in any medium, okay, deriving the vector Helmholtz general equation and then deriving these constants. That is how you proceed. Okay. Now, along with this, there are some 2-3 terms that you need to know. Okay. The first term is skin depth or penetration depth. This skin depth. So these are basically terms which are associated with good conductors. Okay. These are all terms associated with a good conductor. So, see now, as E or H wave travels in a conducting medium, what happens? The amplitude is getting attenuated by a factor e raised to minus alpha z. Okay. So there is a distance, okay, a distance del through which the wave amplitude decreases by a factor e raised to minus 1. E raised to minus 1 is 1 by e. That means about 37%. And that is referred to as the skin depth or penetration depth of the medium. Okay. That is E0 e raised to minus alpha del becomes E0 e raised to minus 1. So what is the relation? The skin depth is a measure of the depth to which an electromagnetic wave can penetrate the medium. This is important. What is skin depth? It is a measure of the depth to which an electromagnetic wave can penetrate the medium. And this is valid for any material medium. Okay, this expression here, 1 by alpha. For good conductors, okay, in place of alpha, when I substitute this, then I get equation 10.54b. So this is specifically for good conductors or perfect conductors. Okay, so see this figure that we're talking to about, the figure 10.8 that we're referring to, this is the figure. So here if you see the distance, okay, through which this amplitude is attenuated to approximately 37%, as you can see. So that is referred to as the skin depth. It is a measure of the depth of penetration of an electromagnetic wave into a medium. Okay. So knowing the skin depth is important. And another thing that you need to know about the skin depth is that it basically varies with frequency. Okay. And for conductors, the skin depth is going to decrease with increase in frequency. How does it vary? The skin depth will decrease with increase in frequency. So see there again, using a couple of equations, again the intrinsic impedance for a good conductor can be simplified. That is, in terms of skin depth, it can be simplified in this way. Okay. These equations are taken from the Sadhku textbook. The chapter is electromagnetic wave propagation. Okay. So just look into the textbook, electromagnetic wave propagation. Under that, the section on plane waves in good conductors. Okay. So this is just a substitution. See, there are basically 3 equations that we need to consider in order to get this. The first equation is this. The equation for alpha is equal to be this one. This 10.51a. Okay, so we are using this equation. Then we are also using this relation that your del is equal to 1 by alpha. Okay, this equation is also used, and we are also using this equation. So using these three equations, when you rearrange, okay, yeah, sorry, we are writing for intrinsic impedance. So this equation is also needed. That is, we are using 10.52, okay. In equation 10.52, we are going to correspondingly substitute in terms of 10.51a and 10.54b. This equation here. Okay, so just write down these three equations and substitute, and you will get this. See, once you get 1 by sigma del root 2 e raised to j pi by 4. Okay, when you substitute, you will get this. And how do you get it as 1 plus j? See, how can you write this? You can also write this as root 2 cos pi by 4 plus j sine pi by 4, isn't it? And pi by 4 is 1 by root 2. So the root 2 cancels out. That is how you get this particular expression. So if I'm substituting, okay, in terms of, that is, instead of writing e raised to minus alpha z, in place of alpha, if I substitute 1 by del, okay, and similarly here in place of beta, since alpha is equal to beta for a good conductor, okay, when I replace, the expression for E can also be written in this way. So from this particular expression, what do you understand about the skin depth? It measures the exponential damping of the wave as it travels through the conductor. Okay, so I have not for copper at various frequencies, the table is there in the text. Please refer it. What you can infer from that is, with the increase in the frequency, your skin depth is going to decrease. So what does that imply? E and through good conduct, it is very difficult for E and H to propagate through good conductors. And that is true, isn't it? For a conductor, for a pure conductor or a perfect conductor, will you have electric field inside? No, E is 0. Okay, so that is justified in terms of the skin depth. Okay, and yeah, so that is the concept about skin depth. Now, the next concept is this. The skin depth concept is again useful in calculating the AC resistance due to skin effect. Okay, so first we'll calculate the DC resistance, and from there we'll go to the AC resistance. So DC resistance is L. L is actually the length of the conductor divided by sigma S. This is the expression for the DC resistance. Okay, S. And so skin depth is useful in calculating the AC resistance due to skin effect, which means another concept that we need to discuss is the skin effect. Okay, so as I told you, these are concepts which are mainly applicable only for the perfect conductor. Okay, so the first case was the skin depth. What do you mean by skin depth? How it varies with frequency? Okay, and all the other details about skin depth. Now, skin effect. Okay, so what do you mean by skin effect is the fact that in a conductor, your field intensity in a conductor will rapidly decrease. That phenomenon is referred to as skin effect. That is, there is a tendency for the field and the associated currents to be confined to a very thin layer of the conductor surface. Okay, like for example, if you have a wire of radius A at higher frequencies, okay, it is possible to assume that your current is going to flow only through a small ring of thickness rho. See, this fact is already known to us. Okay, for a very good conductor, the current is going to flow only along the surface, or the current is more concentrated along the surface. So various situations where the skin effect is observed are attenuation in waveguides, then in the measurement, or it affects the AC resistance or the effective resistance of transmission lines, and again in electromagnetic shielding also. Okay, and a couple of applications where the skin effect is taken to an advantage are in pure silver and in silver plated brass component. What happens is, because the skin depth is very small, the difference in performance is negligible. So silver plating is often used to reduce the material cost. And hollow tubular conductors are used instead of solid conductors in outdoor television antennas. That is again because of skin effect. Okay. And normally, for all electrical devices, effective electromagnetic shielding is provided by suitable enclosures. Okay, so this is a representation of how at higher frequencies the skin depth is less, first of all, and your field and the associated currents are confined to a very thin layer of the conductor surface. So this is what you're supposed to know about what do you mean by skin effect. Okay, so far we have discussed skin depth and skin effect, and now we are coming over to the part about the resistance. So an expression for DC resistance was shown earlier. This is the expression. Now we're particularly going to define surface or skin resistance. So the unit is in ohm per meter square. Okay, and this is defined as the real part of the intrinsic impedance for a good conductor. Okay, intrinsic impedance is measured in ohms, and the real part of the intrinsic impedance for a good conductor is defined as surface or skin resistance RS. So in place of L, I'm going to write it as 1. That means, how can you define this? It is the resistance of a unit width and unit length of the conductor. Okay, and it is equivalent to the DC resistance for a unit length of the conductor having a cross-sectional area 1 cross del. Okay, so basically what you need to know is this definition: the resistance of unit width and unit length of the conductor. That is what you mean by surface or skin resistance. Okay, and so for a given width and a given length L, the AC resistance is calculated using the DC resistance relation itself. Okay, in 5.6, that is the previous expression that we just wrote. And if we assume uniform current flow in the conductor of thickness del, so this is the effective AC resistance. Okay, and that is expressed in terms of the DC resistance. Yeah, sorry, it is expressed in terms of the surface or skin resistance RS. Okay, and the ratio of AC to DC resistance is given by this particular expression. Okay, the ratio of AC to DC resistance. So see capital S in the expression for DC resistance, it actually stands for the area. Okay, so with this, we've come to the end of this lecture. So to summarize, we started with some basics on applying phasors to electromagnetic fields. Okay, and then we have come to the wave equation, the Vector-Helmholtz equation. Okay, generally derived for lossy dielectric, but it is applicable for all other media. Only thing, we need to properly substitute the expressions for alpha, beta, the velocity of propagation, the intrinsic impedance, and the wavelength, and the expressions for E and H need to be correctly obtained. That's all. So for different media, that is the lossy dielectric, lossless dielectric. Lossless dielectric is also called as perfect dielectric, free space, and then a good conductor, which is also called as a perfect conductor. For all these different cases, the several constants were defined. Okay, see the definition of attenuation constant, phase constant, and all is also important. I did not specify the derivation here again because it is already discussed in lecture 2. Okay, And then particularly in conductors, we discussed about skin depth, skin effect, and the surface or skin resistance, effective AC resistance. Okay. So with that, I'm concluding this lecture. Thank you.